Let us talk about stationary points in partial differentiation. But before we go to partial differentiation, let's review what we did before in total differentiation. When you had f of x is equal to some value in x, right? X squared, or it could be x cubed plus 2, whatever it is. You had f of x alone. So you might have had a maximum point, minimum point, or what is called a point of inflection. Alright? So you have a line, and that line, if it touches the curve at any point, you say it is a tangent to the curve at that point, which you call the point of tangency. Alright? Now, you have a certain point on the curve where the tangent is horizontal. And you know that the gradient of a horizontal line is 0. This doesn't look too horizontal. Alright. I want to have this horizontal. Okay. Let's use this line as our horizontal line. No. The gradient is 0 at that point. That's a maximum point. Right? You might have a minimum point where the gradient is also 0. Or point of inflection where the curve does not turn. It goes from positive to negative, or towards negative, but it doesn't go into the negative direction. The curve gradients go from positive to 0, then back to positive. Or they may go from, say, negative to 0, then back towards negative. Those are points of inflection. Remember those. So, in those cases, you have the tangents being horizontal line, even though at the point of inflection, these lines cut through the curve, so they're not really tangents as such. It would be only tangents if you divide up this into a left and a right section. But these are two tangents. So you remember that the gradient is 0, therefore the value of the gradient function dy by dx is equal to 0. So in order to find where the maximum or minimum point was, we differentiate once, equate to 0, and you are able to find the x and the y values where the maximum or the minimum point were located. Alright. After that, you remember that if you were to find the second derivative, d squared y by dx squared, you're able to tell the nature of a stationary point even without the graph. If d squared y by dx squared was greater than 0, in other words, positive, that was a minimum value. Alright? Because remember, as you go from left to right, well, it's supposed to touch the curve. As you go from left to right, the tangent turns from negative to positive. When you pass the minimum point, right, you see it turning upwards. The tip of the line will be curving this way. So it's a positive, right? So in this case, you had a minimum point. Then what happened at the maximum point? D squared y by dx squared is less than 0. In other words, when d squared y by dx squared is negative, you have a maximum value, right? It gives you an idea where the tangent is turning, the gradient of the tangent is going. So it is going this way to the negative, so it had a maximum point. Alright, now let's look at the stationary points when you have a situation that says f of x and y. So in this case, it's x and y. So remember, when you had f of x is the same as y equal x. So you have an x and y axis. When you have f of x and y is the same as saying z is equal to x and y together. So you have an x, y, and z axis. So you're looking at 3 dimensions now. Alright? Now let's take a look at a few diagrams that will help us visualize what's going on here. So I'm going to copy this and paste it over here. Now, here what we have is our x-axis from this going this way, our y-axis. So, well, x-axis, this is a 0, so it's going negative and positive. Our y-axis, this is 0, going negative and positive, and our z-axis, 0 is here, going negative and positive. Alright? Now, this line is a change in y, the blue line, and this line shows a change in x. Right? Now, the red line is f of x, shows x changing. The blue line is f of y, show y changing. And then z, of course, is up and down. Now, here, if you are right here at the maximum point, right, any direction you move, you'll have to be going down. You can see that. So it shows you that it's a maximum point that you have. So one way to determine the maximum point is to find a point, whether it's maximum or minimum point, is to find a point f of x, y, but you specify it to f of a, b. Suppose I ask you, is the point, this point, is either a maximum or minimum point? How can you tell? Well, what you do is add something to A and add something to B, right? So, if you say f of A plus h, B plus h, and let's not bother with the brackets here, f of A plus h comma B plus h, and then you see that it is less than f of AB, then you know you would be going down. So it's a maximum point. If f of A plus h, where h is something added to A, and B plus h is something added to B, if it was higher, then A would be here, A plus h would be here, or here. Same thing with B. So if f of A plus h is higher than f of AB, then you know you'd be at a minimum point. Alright? But here, what we want to look at is what happened at the minimum or maximum point. Let us say this is our tangent to y, and this is our tangent to x. Alright? Now what you will see is that both of them have a gradient of 0. So if you call the function f partial derivative, we do that again. So partial derivative of f, which is pec to x, equals 0, and the partial derivative of f, which is pec to y, equals 0. Alright? You see that? Now, to locate where the stationary point, or the maximum point, or minimum point, whatever point it is, what you do is to equate the partial of f with respect to x and the partial of f with respect to y. Alright? Wherever they are 0, solve them simultaneously. Alright? So we're going to look at examples later on. What you do, equate to 0, then solve. You would have two equations into one node, so it would be a pair of simultaneous equations. So you solve them simultaneously. That will give you the solutions, the coordinates of the stationary points. Right? Now the thing is, you want to know whether you have a maximum or minimum point. Now we're going to look at the situation with a minimum point, but I have 3 diagrams. One is a maximum, which is this, the other is a minimum, and then there's a saddle point. I had copied all 3 of them here at once, and then the program crashed. So I don't want to do that. Let's look at them one at a time. Now, suppose you consider what we said before about the earlier integration, or differentiation, I mean, where d square y by dx squared was greater than 0. That means it's positive, meaning you have a minimum point, or less than 0, meaning you have a maximum point. Let's see how that would apply here. here what you have is that if you take the second derivative and say delta square f by delta x squared, if this here is, in this case, it would be less than 0. In this particular case, it would be less than 0, right? In other words, it is negative. Now what about delta square f by delta y square? I'm still not fully recovered from the flu, so while talking I have to be coughing, right? And of course my voice isn't that up to date as yet, hasn't fully recovered. But you will find that delta square f by delta x squared is also less than 0, which is negative. Alright? Remember that as you go in the positive direction along x, you would have tangent going from this to this to this, going towards a negative. So here you know that is a maximum point you have in the x direction, and as you move in the positive direction of y, the tangent, the various tangents that you can draw would be falling. Their gradients would approach negative. So delta square f by delta y squared would also be negative. So confirming that you indeed have a maximum point. Alright? So in that case, you would have a maximum point. Now, both delta square x, both second derivative, or let me say both second partial derivative, both of these second partial derivatives are negative. So this thing keeps popping up. When you have both second partial derivative are negative, the point is a maximum point. Alright, so there you have that. We'll look at the minimum point in our next video.